Morning, Emanuele is going to talk about sampling orders.
Thanks. So when we talk about lower bounds, we usually mean lower bounds for computing a function on a given input. This talk is going to be about a different type of lower bounds, which I'm going to call sampling lower bounds. Okay, so here the setup is that you have some distribution in mind, and you want to know how difficult it is to sample that distribution, say just given random bits. There's many reasons why I think this is worthwhile. In mathematics, it's often common that if you have a difficult problem that you cannot solve, you can try to solve a harder problem. So in general, this thing is a harder thing to understand because there's many non-trivial ways in which you can sample distribution. I'm going to give you several examples of that. There's been a fair amount of papers until now. Some connections have been established to other areas, but generally still in uncharted direction. And I'm going to give you a bunch of open problems. I'm just going to touch on a couple of connections. So some of the ideas and results that were developed here were actually used in the two-source extractors breakthrough by Chattopadhyay and Zuckerman, and later, more specifically, in the tightening by Benaroya, Doron, and Tashma. And there is a connection to data structure lower bounds, which I'm going to touch on later in this talk, but I think it does not yet given very strong bounds. Okay, so the bulk of this talk is going to be about AC0, but before that I'm going to mention a couple of simple problems on decision trees, okay, because I want to give you a sense of the breadth of problems and techniques in this area. So let's start with the problem about trees. So here I just want to sample Hamming slices. Okay, so let's say that S is the uniform distribution over m bits with Hamming weight half. Okay, and I want to sample this distribution via a function that maps some input strings of any length to n bits. Okay, and each output bit of this function is a small depth decision tree in uniform bits x. Okay? So the depth of this tree is d, so I'm going to call f depth d forest because it contains several trees. Okay? So you can hope to sample this thing exactly, but you may ask how far do you have to be from this distribution, and we measure distance in terms of statistical distance between the distribution S, the target distribution S, and the output of f on a uniform input x. Okay, so the statistical distance is a natural notion of distance of distributions, which is written here. So it's how well a test can tell it to distributions. It's the maximum overall test T of the chance that one distribution lands in T minus the other one landing in T. It's a number between 0 and 1. Okay, so if they are identical, it's 0. If they are disjoint supports, you can get very close to 1. So there is an argument that can give a lower bound of 1 over through the AD. I'm just going to sketch it in words. So how do you prove this thing? Well, let's look at 10 bits of the distribution. Okay. So here, these 10 bits are very close to uniform. Okay, not exactly, but very close. So they should also be very close to uniform in F. Okay, if they're not, then because they're sampled by a small depth tree, they must have a distance from uniform, which is at least this, which is much bigger than that of S, and so you get this lower bound. Otherwise, every 10 bits are exactly uniform. And then you can apply central limit theorems for bounded independence, in particular anti-concentration, to argue that the Hamming weight of this is unlikely to be exactly n over 2. Okay? So at least you heard some buzzwords of what goes on there. And you can ask about lower bounds, and actually you can reinterpret some nice works on switching networks by Chumai and other people, to show that just with depth log n, you can get very close to this distribution. Okay, you can actually simulate a switching network with such trees. Okay, and so an open question is, what is this quantity? Okay, so even for constant depth, can you prove that for depth 10, this distance at least half? Okay. This question is actually connected to some questions in data structures of storing sets, okay? But I'm not going to say too much about it. But if you can prove some very strong bounds here for some variants of this question, you will actually get some lower bounds for the data structure problem of storing sets. Okay. I want to mention another simple question. And that's the question of storing permutations. So let's say pi is a uniform permutation of the elements from 1 to n. Okay, so just think of an array of elements. Each element is within 1 n and the other permutation. Okay, and I want to sample pi, again by a decision tree, decision forest. So now each query of the tree will be an element within 1 and n. So the children of each node are n, as opposed to 2. And it's not even known what's the statistical distance if the tree have depth 2. So each tree here just makes one probe to uniform bits, and then based on that it's going to make another probe, and it's going to output a value within 1n. And this whole thing should be very close, should be maybe close to uniform permutation or not. So if you go prove a lower bound, the statistical distance, that's the connection to data structure that approaches 1. You will get a lower bound for storing permutations in a data structure model. These bounds are known for non-adaptive trees, but even if you make 2 adaptive probes, I don't know how to prove them. So hopefully someone
But you need much higher depth to get a good data structure lower bound.
Yeah. So 2 would just give you a lower bound for 2 cell probes, so which is unknown. So it's consistent with, at least my knowledge, that you can store permutation with 0 loss in space and answer each query with 2 probes. I don't know how to disprove it. The best upper bound is like log n. Actually, I'm going to give you later in this talk a very nice, I think, upper bound for AC0 for sampling permutations. Okay, so now I'm going to switch to AC0, though we will come back to trees for some lemmas. So I'm going to draw these circuits with the input x up top and the output y at the bottom, and typically the output will be more than 1 bit because I'm sampling distributions. So although these circuits cannot compute parity, they can do something which is almost as good. They can pretend to be computing parity. They can generate input-output pairs of the parity function. Okay? And this is something which was pointed out by Babai and Bopana and Gregarias 3 years ago. And it's a simple construction that actually you can do over any group. Okay? So I just see exactly what I mean. So I claim that there is a function that maps just n bits to n plus 1 bits. That's in AC0. In fact, it is just locality 2. We'll see in a second. And the output distribution of f over a uniform input will be exactly the distribution y, comma parity y for y a uniform input. Okay, so it's exactly generating a uniform input together with its parity. And as I mentioned, it's just a standard, in hindsight, telescopic trick. So here is the input. The first output bit will just be x1. The second output bit is going to be x1, XOR x2. The third is going to be x2, XOR x3, and so on, up to yn. These n output bits are completely uniform, as you can check. But the nice thing is that if you XOR them, you just get xn. So you can just output the parity in clear here. Okay, so this actually achieves statistical distance 0. Okay? And you may think, well, okay, so it's this thing, so whatever. Well, actually, you can do a little bit more. So in Pagliazzo and Naur, we were able to show that you can even sample y inner product of y. So it's a little bit more complicated, although it's a similar idea. So you build on the previous result. Something which I find quite exciting, actually, it's a very different construction, which I'll show you in a second, that you can sample permutations in AC0. So AC0 can sample something which is very close to a uniform permutation over n elements. And this thing has to have some small error because the permutations are not a power of 2. You can use this result to even do other things, like you can sample, for example, input-output pairs of any symmetric function. So you have AC0 circuits which can generate a uniform x, a uniform y together with its majority. Okay? With something which is I find much less obvious than the parity example. This thing is going to use that, and so it inherits this error. But it's conceivable that you could do this thing with error 0. So as an open question for you is this. So can you sample y majority y exactly in 0? And I think it's something that you can attack tonight without any background besides what you have. I think that people just have no idea to prove these things. So I think it's conceivable it may be possible because the error here is actually of a ZPP type, so you even know if you make a mistake. So condition on a small event that you can recognize in S0, you would sample exactly permutation. So if there was a way somehow to recognize the event, and just in that case, massage a bit the probabilities and make everything fit nice, you get error 0 here. But I tried for a while and I couldn't do it.
Would it have any consequences?
To me, a lot. I don't know. So, I don't know this result. I think, I don't think of anything spectacular. Okay, so I want to tell you this. Is there anyone here who knows this thing? Sample permutation thing 0?
You know,
okay.
So there was an earlier thing of now and
doing this? So this is from the 90s, so I am not aware. They didn't cite them.
Maybe it was not, I don't know.
Okay. Yeah. So is there anyone who knows it? So if you haven't seen it, I think you like it. I mean, I really like it. So you can find a streamlined exposition.
So if you've seen it, you like it.
You can find a streamlined exposition in my paper. They do it in the context of pirams and so on. Okay, so what are we doing? We want to sample a vector of n elements which are permutations. Okay, so just a vector in a certain way. Each entry is going to be an element between 1 and n. Okay, in S0. So the basic idea is to do dart throwing. Okay, so we're going to have the numbers within 1 and n, and we're going to place them in the array from 1 to n uniformly at random. Okay, let's start with that. So here's my elements. These things are not random now. Okay, so these are just the fixed element 1, 2, 3, 4, 5. I'm using my random inputs. Okay, in S0 to find random locations in a target array. Okay, and this thing can be done in S0. Okay. Okay, so if there is no collisions, then I'm done, right? Then this thing is exactly by symmetry permutation. Good. Okay. Of course, there will be collisions, right? If you throw n things into n slots, there will be collisions. So some slots are going to be empty, some slots will be overcrowded, and so on. Okay, and this thing is a problem. So what you can do? Well, okay, so let's get some room. Okay, so instead of throwing darts into n slots, let's throw dart into m slots for m much bigger than like n squared. Okay, so you enlarge the array, and now there's going to be collisions. Okay, and then I just need to remove the empty slots.
You said that the error is exponentially small in n.
What's the error? Well, okay, so the error, you can make n to be n squared, and the error will be exponentially small, m cubed. So, I mean, the chance of a collision will be just ignore that. So I just need to remove the slots here. Can you remove the slots? No. Right. That's impossible, right? You can remove the slots. So that would mean that they will need to place 5 at a location which is how many non-empty slots you have here, which is impossible to count in S0. So the key insight is the next one, which is I'm going to think of permutation in a different way. I find this thing really fascinating. So I'm going to throw darts in exactly the same way as I described, but I'm going to think of a permutation in a cycle format. Okay, so a cycle format is just the familiar one, and the cycles are going to be written in a specific way. So each cycle is going to start with the least element in the cycle, and the least elements are going to be sorted. So here I have a 2, 3, so 2 will be the least element, so I know that the cycle is 2, 3, then I have 1, so this has to be next cycle. Okay? And what you need to do now is to be able to compute the next element in a cycle in S0. That will allow you to actually output the permutation. And this thing can be done because you can identify in S0 the beginning of cycles. So how do that? Well, the beginning of a cycle is an element which is smaller than anything else that comes before. Okay, so 1 now is the beginning of a cycle. Once you know that, it's easy to find the next point. If you're at a beginning, if you're not close to a beginning, you just go forward, and otherwise you go back to the previous one. Okay, so now you can find the next one, and you can just output the permutation. That's how you sample permutations in S0.
But do you get the uniform distribution?
So condition on no collisions, yes. So if you have a collision, then you have a collision, and then you just abort. But you can recognize if you have collisions or not. So you can opt through something with that.
It's a canonical representation. There's a unique representation of each permutation as a set.
Oh, yeah, yes. So by symmetry. So yeah, you can verify that it's yeah. So you have to verify that imposing this this doesn't.
Oh, I see.
Yeah, but you can verify that.
What do you mean by least element sorted? Or?
So each cycle will have its least element first, and you're going to write cycles where the one which has the top least element among all cycles, it comes first. So here I have to write down 2, 3 first, and then I have to put 1, 5, 4. Okay, I cannot do it the other way around.
So what's the output format actually?
What's that?
So what's the output format?
The output format is just a spring array of elements from 1 to n. So given this, then I have another step. Then I have to find. So then to fill. So the position 1 of the array will be 5. So in S0 I'm going to look for the next element. The position 5 will be 4, and so on. Okay, so I have another step to do that. All right. So this arguably explains why it's difficult to prove lower bounds. So let's see what you cannot do in S0. Okay, so what lower bounds can you prove? So one lower bound that was shown, first one actually, was for sampling error correcting codes. This is in a paper with Chagar, and then it was improved by back in Pagliazzo and Grovette in a way which I'll mention. So here you have a good binary error correcting code, asymptotically good, and let's say Z is a uniform distribution over code words. Let's say that you have an S0 circuit which takes some input bits and output a string of n bits. Then you can show that the statistical distance within Z, a uniform code word, and the output distribution of the circuit is exponentially close to 1. Okay, so in the original paper we had polynomially close to 1, and then with some nice idea about deviation bounds for small depth forest. Back in Pagliazzo and Grovette, actually they improved it to exponential. Okay, so this result gives a very strong bound, like it's exponentially close to 1, but it's really tailored for codes. Okay, it doesn't apply to other distribution. In particular, it doesn't apply to things like input-output pairs or Boolean functions. Okay, so later it was possible to get lower bounds even for this input-output pairs thing. So it was shown that if f is a Boolean function, which is a bit block extractor, so it's an extractor for a type of source which I'm going to call a bit block, which I'll show in a second. Some things that we know how to construct. Okay, it's not too important now. Then S0 cannot sample input-output pairs of this function. Okay. The statistical distance is bigger than 0. And then recently we improved this result to something very close to half. Okay, so for the same function, it's possible to show that the statistical distance will be superpolynomially close to half. So half is the best that you can opt for, because either a uniform y and 0, uniform y and 1 will have statistical distance half. So this gives a function that you cannot compute much better than tossing a coin, even if you can sample the input yourself. Okay, something which wasn't known. the circuit gets to sample the input and it still cannot compute the function, much better than tossing a coin. Okay, so in the rest of this talk, I'll tell you some the techniques that go into these two results. Actually, I'll start with the first, and then the second one builds on the first. All right. So for the first result, the main theorem is this one: is a characterization of distributions that you can sample in S0 and that have high min-entropy. So the min-entropy of a distribution is just its worst case notion of entropy as opposed to average case and notion in shell entropy. The min-entropy is at least k if every string has mass at most 3 minus k. Okay? So the theorem says that if you have any circuit whose output distribution has min-entropy at least k, then the output distribution of the circuit is very close to a convex combination of much simpler sources. So it's something I'm going to call bit block sources. And moreover, these things have high min-entropy also. The min-entropy is k squared over n to the 1.01. It's not important, but basically, when k is a bit larger than root n, then you still have a lot of entropy in your sources. Okay, so if the circuit is sampling something which has min-entropy larger than root n, bit larger than root n, then actually you will still have high min-entropy bit block sources. So bit block source is a special case of a fine source. It's a string of symbols where each symbol is either a fixed bit or it's literal. So it's 0, 1, Z5, it's a uniform bit, 1 minus Z3 is the complement of Z3, Z3, and so on. You can think of these as just a fine sources. There actually are results that we specifically use the bit block structure, but in this talk you can just think of them as a fine sources. Okay. So we know how to build extractors for these things now, especially now, much better than before. So as a corollary of this theorem, I want to show now why the circuit cannot sample input-output pairs of this function f. Okay. So here is the proof. We do proof by contradiction. Assume that you could sample this thing exactly. Then in particular, the min-entropy of the output distribution of C is very large because this thing has min-entropy n. Okay, so the min-entropy of X will be n. Okay. So by this thing here, you can write Cx as a convex combination of these bit block sources. Now there is a step that I'm just going to hand wave. You can basically fix the bit that correspond to f of y here by fixing some bits, some input bits while leaving high min-entropy. And then you're left with a high entropy bit block source, but the value of f is fixed, and that contradicts the extractor property. Any question? Okay. So, yeah. Just a heads up that this thing actually only gives statistical distance more than 0, but not even 0.1. Okay, because this step here, if C of x was a closest statistical distance to this thing here, it's not clear. In fact, it's false in general that the min-entropy is large. Okay, and we're going to have to fix this thing later. But for now, I want to.
If we fix the value of fy, and
yes.
Will the new source still be a bit block source?
Yes. Yes, you can, because yes. So basically, it will be just fixed in some of these bits here. So I mentioned this thing in detail, but basically, you can fix just this portion because now it has a very simple structure. It remains a bit block. It remains with high entropy, and that's impossible by the extractor property. Thanks. Okay, so I want to show you the proof of this theorem. Okay, so this is a characterization of high min-entropy AC0 sources. And the proof is done in 2 steps. In the first step, we'll do it when the circuit is actually not just 0, but it's even d-local. So each output bit will just depend on the input bits. And then there is a way to reduce AC0 to this d-local setting. the way it's done is via the switching lemma. So we use random restrictions. So the switching lemma will collapse C0 to a D-local function. And the new ingredient is that we are going to have to guarantee that the entropy is preserved. Okay? So let's first see this. So I have this one slide with the proof, and I just want to spend a couple of minutes on this, also because I want to ask you a question. So just take a deep breath and go through it. So what am I doing? So here are some uniform bits. Okay, x1 through some element here. I have my output distribution. It are n bits. Okay, and this thing is d-local. Whereas the min means that each output bit here just depends on the input bits. Okay, what am I trying to show? I'm trying to show that this output distribution here, the y's, can actually be written as complex combinations of these bit block sources, in which we just have these blocks of things which are independent and just depend on one bit. Okay. With high entropy. Okay, so how is this thing done? So the first step is that without loss of generality, I can also ask that the degree of the excess is small. So how small? Well, I can ask it's 2nd over k. So you have d times n edges in this graph. The number of excess which has degree larger than this is at most k over 2. So if you can just fix those k over 2 excess, and because you have min-entropy k, that's just gonna still leave you with min-entropy k over 2, and that's good. Okay? So I can assume that this degree is small. And now the argument is this. So because the output entropy is still large, it's still omega k, it's k over 2 now, you can show that some of these bits here has to be somewhat uniform. Specifically, you can say that the variance is at least k over n. Because if you have k bits of entropy here, you have n bits, one of them to have variance k over n. By an isoperimetric argument, if this thing has a variance, well, then one of these bits here that are the input of this bit here must be somewhat influential. So the influence will be the variance divided by d into d, because there's d bits here, one of them has to at least influence variance divided by d. Okay, so you have some bit here which is influential, is xj here, and now the idea that basically is that you want this guy to give you a block. Okay, so the way it's done is that you're going to think of sampling the excess by first sampling the neighborhood of the neighborhoods of this xj except xj. So this takes a bit to visualize, but I think you've seen the idea. So once you do this, the neighborhood of this bit here will just depend on this bit because you fixed anything else. Okay? And this thing with the probability that comes from this influence bound is still alive, means it's still going to affect the block. Okay? So that's going to give you one block, so one bit of min-entropy. Okay? And because you fix things in this way, you can actually repeat the argument. So you can iterate, you can find another yi now, repeat the argument. You will not have any interference because you fix this neighborhood of the neighborhood. So you took care of anything positive that could be shared. Okay? So so probability, which is this influence bound, this neighborhood of xj is one block which is alive of this size. Okay, you can repeat a number of times, which is the entropy that you have divided by how much stuff you're fixing, which is the size of this neighborhood of neighborhood, which you know exactly how to bound because one thing is d and the other thing is this nd over k. And so, you know, you can do a consideration of measurements that you will expect some number of blocks, okay, and you get some number of blocks with high probability which are alive, and that's the proof. Is there a question? Okay, so this bound is worse than the one that I had before, but you can change things a bit. Okay? So one question that I like very much is do this for trees. Okay? So this thing is true for decision trees. So it is true if you use the switch lemma. You can actually hit the tree with the switch lemma and make it local. But that gives you much worse bounds, okay, in terms of error. And this is, okay. Is it true that a d-depth tree source can be decomposed in this way? Actually, many of the steps here, in fact, in some sense, the more conceptual steps, they go through. So this is still true. The isoperimetric actually is still true. So there is this nice work by anyway, some people here that still gives you influential bits. But somehow these technicalities of doing this type of restrictions here in terms of like degree, that what doesn't work, and it's not clear how to fix it.
You could do it with 2 to the d. You want to,
yes.
you
Yes.
want to
Yes.
stay polynomial
Yes.
in d.
Yes. Yeah. Of course. Yeah. When do yes. I want the same parameters with d3, and I don't know that it's false. Okay, so that's the question for 3, and it actually will give better bounds, better error bounds for the sampling error bounds. Okay. All right, so we've done this. So it was a bit technical, but I think you've seen how you can just argue about these like local samplers. So now, to handle generalized zero circuits, as I mentioned earlier, we're going to use random restrictions. This is going to make the circuit local. The new ingredient here is that I want to preserve the entropy. Okay, so and main lemma here is a lemma that says that for any function, so if you have any function whatsoever on some inputs that outputs n bits, whose output distribution has min-entropy k. Okay. Then if you hit it with random restriction that leaves each bit alive with probability p, then the restricted version of the function has min-entropy pk. Okay? And that's the best possible because the function could just copy the input in the output and will give entropy pk. So if you have this plus the switch lemma, you can reduce a 0 to local and then use the previous result. Okay? And you will get sampling error bound. So the proof of this is by bounding the collision probability of the restricted version of the function. The main step in this proof is actually something I want to spend a couple of minutes on, is what I'm going to call an isoperimetric inequality for noise. Okay? It's something that appeared in this paper with Troy and actually was used in many of the papers in this area for some reason. Okay, and is this result here. So let's say that you have a set A of density alpha, okay, and you pick a uniform input x, and then you pick a noise vector n, where each bit is 1 with probability p, okay? And now you want to know what's the chance that x is in A, and also the noisy version of x plus n is also in A. Okay, so you have these two correlated copies. So this quantity is always at least alpha square. You can prove this by Cauchy-Schwarz. That's not important for us. It's always at most alpha, okay, just because the chance that x is in A is at most alpha. Okay? So the content of this is that you can actually gain a factor of alpha to the p, which is critical for everything. Okay? Once you have this, you can bound the collision probability with some norm inequalities, which I'm not going to show. Okay? But I want to give you the proof of this thing because it's a two-line proof in hindsight. Okay, so here is the isoperimetric statement again. Okay, so you have set A, x and x plus n, and the chance that they both land in A is at most alpha to the 1 plus p. Okay, as opposed to just alpha. Okay, so you get a bit more. So that's the proof. So let me actually switch to characteristic functions. So let me set f to be the characteristic function of A. Okay. So what I need to bound is the expectation over x and n of the product of f of x and f of x plus n. F of x is Boolean, so it's 0, 1, so n will be just the product. Okay. Okay, so let me just bring inside the expectation over n, so the expectation over x of f of x times expectation of n of this. Okay, and now I'm in good shape for doing Cauchy-Schwarz. So this is just the expectation of some A times B. So I can do Cauchy-Schwarz, and I get the square root is at most the square root of the expectation of x of f square x. Okay? This is just one term, so it's very separate from the rest. So times the square root of the expectation of x of the square of this. So the expectation over n square, this. Okay, and now the second step in the proof. So this thing here is the L2 norm of the noisy version of f. So you can apply hypercontractivity. Hypercontractivity is a result which allows you to trade noise for the norm. So specifically, you can relate this to the norm of f, and the norm is not 2, but it's 2 minus order of p. Okay, so you go from L2 norm of the noisy version of f to the 2 minus order p norm of f. Okay? The first term remains the same. Now, because f is a Boolean, all these f are just 1. So what you get here is this is the square root of alpha. Alpha is the density of the set. And here you get, this is just 1. So you get alpha to the 1 over 2 minus order p. Okay, and so you get square root alpha here, and here you get square root alpha plus a little bit from this, and that gives you that. Yeah.
So isn't it just small set expansion?
Just what?
Small set expansion?
I think you can view it as a small set expansion.
You can also split them out evenly, and then you don't have to do Cauchy-Schwarz. You can save the step.
So there is actually, it's possible to give a tighter proof, which would be tight for some sets, which I'm not shown here. So you just do some free analysis, and so I'm not sure if what you're saying would be a simpler proof than this, or maybe.
The small set expansion for the QB is proved using the hypercontractivity.
So I mean, this is partly tutorial, so I'm not claiming this is like, it was published already, so I'm like done. So anyway, I think it's useful to see these things. Okay. Right. So here's a recap or where we are. So we show that high entropy zero sources become high entropy bit block sources. This thing implies sampling over bounds. But they only give statistical distance non-zero. They don't even give you constant statistical distance. Because it's possible that the circuit output a distribution which has a distance, say, 0.1, but the min-entropy of C of x is constant. And let me give you an example of how that can happen. It's a very natural example. So let me consider the circuit C, which on input x, I'm just going to look at the first, say, 4 bits of the input. If they're all 0, is going to output the all 0 string. And otherwise, it's going to sample y for y exactly. Okay, so now clearly, the statistical distance of the distributions, this thing from y for y is just at most 0.1. Okay, but the min-entropy is constant. Okay, because if you just fix 4 bits, you fix the output. Okay, so this is why we couldn't get it in the purest way. Okay, so now I'm trying to overcome this barrier and push the sampling over bound to something very close to half. Okay, so the observation here is that, however, in this example here, if you fix those 4 bits, then the min-entropy polarizes. It either becomes 0 or it becomes very large. So in this case, it's either 0 or becomes n. And it's possible to show that actually this thing happens for every AC0 circuit. Okay? This is actually the general phenomenon. So here is the main polarizing result. Let's go through it, and then someone will explain why I have question marks on the slide. So I claim that for every AC0 circuit, okay, mapping some input to n output bits, you can find a set of restrictions, so it's done via restrictions, a set S of restrictions that accomplish two things. The first one is that they preserve the output distribution, by which I mean that the output distribution of C over uniform X is very close to the distribution obtained as follows. You first pick a random R from S, a random restriction R from this set S, and then you fill the stars at random. Okay? If you do this, you would just get distance epsilon. It's epsilon is like 0.1. Okay? And simultaneously, the min-entropy is polarized, meaning that for every restriction in the set, C restricted to R has min-entropy either 0, so it's fixed, or as polynomial min-entropy. Can anyone explain the question marks?
Construct.
So let's say for simplicity that the circuit has an output distribution which is uniform over half the points. What's strange with this? Okay, so in the case at least, but also in many cases, this thing is trivial, right? So, well, I can just take S to be one input for every possible output of the circuit, right? And this will exactly preserve the output distribution, at least if it's flat, let's say flat probability. And of course, it will polarize, right? Then the circuit is completely fixed. The min-entropy will always be 0. Does it make sense? Okay, so of course I can do this. Okay? Just S will be a bunch of inputs, the circuit is fixed, and the distribution is exactly preserved. So the content of the result is that this thing here actually is not through the n. I mean, it can be made a little bit less. So it's exponential in n minus a polynomial in n. Okay. Now you cannot do this thing from before, right? So you can get away with the set restriction, which is just exponential in n minus a polynomial in n. And this is still going to preserve the output distribution, and it's also going to polarize min-entropy. So now this thing are actually actual restrictions with some stars that will need to be filled, otherwise you cannot do this. Okay. So the proof of this result is kind of like, it goes two steps, kind of like the previous one. So you can argue for local functions and reducers, so, and the template is somewhat similar. And I'm just going to show you one lemma, which again talks about arbitrary functions, not just AC0. And it's a main polarization lemma that I will discuss. So the lemma says that if you have any function whatsoever, then you can find a set of few restrictions. So it's the number of restrictions is expansion n minus a polynomial in n. The function has an n-bit output. And the property is that this restriction will preserve the output distribution of the function. So meaning that the f of x for uniform x will be close in statistical distance to what you get if you first sample an R in S and then you fill the stars at random. Okay? So once you have this, you can do other things and get the result for 0. Okay? But I'm just going to show this and sketch the proof of this result. Is it clear what we're trying to do?
0.9 depends on epsilon.
Yes, possibly. Yes, 0.9 depends on epsilon. So I think you'll get a very good epsilon. Yeah, so I'm not sure. Okay, so let me actually comment on this proof. So the proof is by a probabilistic argument. We're going to pick S as randomly from the set of restrictions which have probability star, say, n to the minus 0.9. Okay, so the usual setting. And the goal is to show that. Okay, so what we show is that if you fix any output of F and you look at the pre-image set. Okay, this is a set of some density alpha. You want to show that with very high probability, over the choice of S, okay, when you pick a restriction from S and you fill the stars random, what you get length in A with probability very close to the density of alpha. Okay? So the probability over S has to be at most 2 to the minus n. The error probability is that I can do a union bound over all possible preimages. And the deviation of this landing in A also has to be exponentially small in n, because I need to sum over all possible contributions of these sets. So one thing is that actually you cannot show that these things are close. You can only show a lower tail bound. But that's sufficient. So if for every set you bound the lower tail, because the sets form a partition of the space, you can verify that actually that each set will be close. Okay? But the important thing is that the deviation here is exponentially small in n, but the number of samples is less than through the n. So we need to handle a deviation which is smaller than the number of samples. Okay, and this requires an argument. So the idea here is that the first thing is that you need to show that this quantity here has small variance. Okay, so it's a sum of variables with small variance, and the small variance here is done via an isoperimetric inequality, like the one that I showed before. Okay? And then you need to use a specific concentration of measured result, which is tailored for small variance distributions. And these bounds actually are, so the upper tail will actually be false. So usually it doesn't matter if you do upper tail or lower tail. So in this case, actually, the upper tail will be false. Only the lower tails are known for these things, but that's enough in our setting. Okay, that's a sketch.
So which concentration bound do you use?
I don't know. So the upper tail is what's known the Bernstein result. The Bernstein has an extra factor in the exponent, which will make this thing useless. The corresponding lower tail, which I don't know if it has a name, it does not have the extra factor, and it can be used here.
So what do you mean you pick S randomly? I mean, you can afford to take all S's of this type, right?
No, you choose location on the slides.
Maybe there's a way of arguing that way. So you're saying just pick all of them with a fixed number of.
Later are uniformity. The number of such S's are this number.
Yes.
Times the.
I don't know if that's.
Choose the endpoint.
Yeah, I don't know if that's. I'm not sure if that would simplify.
I'm just saying the description of S. Is it important that it's a random subset of this size of all restrictions that leave n.9 alive, or it's really all of them? Whether it matters to you whether it's all of them or just almost all of them.
So, I mean, how many restrictions? I mean,
it's this number times, this is the number of variables you fix, times n choose n.9. Sounds.
So, okay. I will need to think about that. Yeah. All right. Yeah. So maybe we can take it offline. Okay, so we just put things together in a minute. So in the end, we prove a lower bound for sampling this y f of y distribution where f is a bit block extractor. I just want to flash how do you witness the statistical distance. So if you give me a circuit C, then actually you want to show that the statistical distance of the distribution is very close to half. So the type of test here that will give this distance is of the form A union B. So A would be the set of those few restrictions that make the circuit constant, they give the 0 min-entropy. That was guaranteed in the previous lemma. And B just checks that this f of y is computed correctly. Just a set of pairs yb where b is different from f of y. Okay, basically, so if you think of this output distribution of the circuit, you're going to think of it as first sampling an R in S, and then thing that starts at random. So when you pick R, if the circuit is constant, then it's always going to land in A, but the target distribution is likely to land in A because A is small. And the target distribution has a lot of entropy, and otherwise C of R has a lot of entropy, and then you can use the previous result. Okay, so the type of tests in the end that guarantee these things are of this type. And you cannot really get away without one of these two, because if you just have A, then the circuit could just output something which lands there. If you just have B, then actually you may not get the statistical distance that you want. Okay, so there's many open problems like the ones that I mentioned, just two more. So one thing is to improve the statistical distance to exponentially close to half. It would be nice to, I think, also to de-randomize this entropy polarization. So if you can somehow construct explicitly these restrictions, it would have some consequences for how many input bits the circuits require to sample this distribution. In general, I think there's more to be done. Thank you. Yeah.
Do you think this entropy polarization works in more general settings, not only AC0, whenever something like random restriction simplifies?
Yes, so it's false for AC0 with parity gates. And so yes, so yeah, so you yes, so it okay, good. So yes, it's an interesting question whether you can relate this type of results to like the shrinkage exponent, and I think so. The previous result about the worst case sampling over bound that can be extended to shrinkage type things. I think this entropy polarization, I was not able to do that because the parameters are not good enough. So maybe something to look at. But in general, if I can extend this conversation, so I think you can think of getting any model that you like or that have been studied here and try to think of what it means. I mean, we've been doing that, right? We started with worst case, and then people are doing average case. So one also not do sampling over bounds for formulas that to threshold circuits and so on. Okay, so I think that will be interesting direction.
In the proof of the entropy polarization, where do you use the fact that it's zero actually?
So I'm not. So this lemma actually holds for every function.
For the min-entropy.
This holds for every function. So as I mentioned in passing, so for the general result, this thing is proved in steps actually, which I will not have shown. But basically, once you have a function with small locality, then you can do it in a similar speed to what I showed area. So you start like fixing things and counting things, how much entropy. So that's kind of like easy to understand. So I have to reduce an AC0 circuit to something like that, something delocal. So that's done via random restrictions. So do restriction.
Yes, but in this polarization, min-entropy, I mean, the theorem says for every AC0 circuit.
Yes.
So where does the proof use the AC0 assumption?
So this thing is like follows. So first you prove it for say delocal functions.
Oh,
okay.
Sorry.
And then you go from zero to those things. So the way you do it is you hit it with random restriction and you use the switching lemma. Mm-hmm. And then you use the polarization to argue that you can use the switch lemma with few restrictions mm-hmm. that don't change the output distribution, the polarize. Yeah. So actually, so this polarization is really only done at the d-local level. Then for S0, you just you find these very sparse set of restrictions which go from S0 to d-local, which preserve the upper distribution, and then you can polarize this d-local stuff.